Stop the recording?
I think he started it again, no?
Yeah, but did I save the other one? What did I do with the other one? Ugh. See, where is that? Well, I will look for it here at the end of the class. All right. Are we recording? Yes, we are. Okay, it's 5, so this is pentanoic. What else is it? It's pentanoic acid. 2-bromo. What else is it? 4-methyl. Pentanoic acid. This other one, 1, 2, 3, 4, 5, 6, 7, 8. So it's hexanoic acid, and it's going to be 2. 8. So octanoic acid, and you got a bromo on 2, 5, and 7. So it's going to be 2, 5, 7, tribromo. What did we say? Octanoic? Octanoic acid. That's an O.
I have a question. Why doesn't the third carbon have H2?
It should.
Right?
Very good. Good catch. That should have an H2. It's missing an H. No one's ever asked me that. That's pretty good. Pretty good catch. Okay, now the 3 on the bottom, 2 of them are the same thing. One of them is not. Look at the left. Let's look over here on the left. What would that be called if there was not a carboxyl group there? What would that be called? Cyclohexane. All right, so cyclohexane, it's going to be cyclohexanoic acid. And these 2 on the right, if the carboxyl group wasn't there, would be called what? Benzene. Benzene. And so we're going to call them benzoic. Benzoic acid. All right? They're both the same thing. They are both benzoic acid. I would definitely make a 3x5 card of benzoic acid. You don't have to do these other things right here, but benzoic acid, you're gonna see that in reactions time and time again. Okay, let's go on to these long-chain fatty acids. Now, in biochemistry, we refer to lipids as fats. What are lipids? Lipids are molecules that are not soluble in water. They're nonpolar. They're predominantly nonpolar molecules. So they're not soluble in water. That's what lipids are. In chapter 17, we'll just kind of gather up all those molecules in your body that are not soluble in water, and we'll talk about them under the category of lipids. Fatty acids are a primary component of lipids. They're the primary building block of triglycerides. They're very important to cell membranes, so to the coating around the cells in your body need these lipids. So fat, we've probably gone overboard trying to get fat out of our diet. There's some doctors out there writing books saying, what you're doing, you're starving your brain. Your brain is 40, 50, 60% fat. lipids. That's what your brain is. So you drive yourself to a very low-fat diet and you're starving your brain. All right? So you do need fat in your diet. Good fat. Good fat.
Can we burgers?
If it has good fat in it. Depends on if they stuffed it full of hydrogenated fatty acids. No. If they're frying your French fries in hydrogenated fatty acids or oils, no. Say no. I don't want that. Give me peanut oil or something. It's not been hydrogenated. All right, so let's look at the difference between stearic acid and oleic acid. Stearic acid is a saturated fatty acid. All single bonds going down through here. CH2, CH2, CH2s. So there are 16 of them. So that is stearic acid. This is stearic acid written out in a long chain. 18 carbons, 1 on each end, and 16 CH2s in the middle. It's an 18 carbon fatty acid. Now, I just told you a little bit ago, this is polar. But this is nonpolar. This is a nonpolar tail, very long tail, nonpolar tail, with a polar head on that molecule. So that is polar, but not polar enough to make this soluble in water. So it's a lipid. It's not soluble in water. Oleic acid is also 18 carbons long, but it has one double bond in it. It's an unsaturated, monounsaturated fatty acid. You've heard the term polyunsaturated? Poly, meaning more than one double bond. So when you've learned about unsaturation, you're learning terms that are on your labels, food labels already. This is a monounsaturated fatty acid. And here would be the condensed way of writing it. You got a CH3, 7 CH2s, CH double bond CH, 7, okay, Jocelyn, did you catch that one?
No, I didn't even.
Okay, that should be a 2. And that one's hard for me to change because that's actually an image that's wrong. That should be 7 more CH2 groups. That's what these are. 1, 2, 3, 4, 5, 6, 7. That's those 7. And 1, 2, 3, 4, 5, 6, 7. It's those 7. They're all CH2s.
Isn't there like a CH3 symbol?
Right there.
Yeah, but
There's one CH3 on the end. Yeah, they flipped it around. So that double bond is actually right in the middle. One other interesting thing about this is that is a cis double bond. You come in on one side of the double bond, you go out on the same side. So this molecule is bent, and that double bond is right in the middle. The double bond is bent. It's got an elbow in it. Okay? The stearic acid is dangly and straight. You know, it can kind of flop around. It's saturated. That long tail is very flexible, but the oleic acid actually has a kink in the middle of the molecule, which is actually necessary in cell membrane formation. So we'll talk about that then in chapter 17. But know these two molecules. The Mediterranean diet. You've heard about the Mediterranean diet. Everybody wants to get on the Mediterranean diet because people on the Mediterranean diet have less heart disease and living longer and stuff like that. What's a component of the Mediterranean diet? Olive oil. Olives, olive oil. They're putting olive oil on their salad. I wouldn't necessarily cook with this. Don't cook with this. If you're going to pop popcorn or fry something, use coconut oil, use saturated oils to cook with, because these things are good at room temperature, but at higher temperatures this can oxidize, and that's not necessarily good. So don't think, oh, it's olive oil, it's good for you, I'm going to use it everywhere. You shouldn't. I'm learning as I teach here. We used to put our olive oil on our salmon and put it in the oven and bake it.
Yeah.
And said, no, I'm not going to do that anymore. I'm going to put coconut oil.
What of avocado oil?
Avocado oil says it. I'm not sure if it's unsaturated or not. It does say it has a high, what do they call that? A high burn point or something. It says something about avocado oil. We've got a bottle of that at home. I'll go read it, the label. But I think it is better for cooking. Okay, so know those two.
What do we have to know?
Know their name and their structure. Be able to draw them. The homework may actually say, draw stearic acid. Yeah. All right, let's talk a little bit about reactions. All right, you know this already. If I wanted to make a carboxylic acid, I could start with a primary alcohol and oxidize it through an aldehyde to a carboxylic acid. You learned this in chapter 13. You can produce an aldehyde by oxidizing this. You could take an aldehyde, oxidize it further, and produce a carboxylic acid. So here is, let's say we want to make this, propanoic acid. Here's propanoic acid. Propanoic acid, we could start with propanol, one propanol, not isopropanol. It has to be one propanol, and oxidize it to propanoic acid. We could start with propanal and oxidize it to propanoic acid. All right, so there's how you could prepare an aldehyde. A carboxylic acid, excuse me. All right, there's one of my favorite slides again, showing the spectrum of oxidation. And notice that the carboxylic acid is on the end. By the time you get here, you could take acetic acid and burn it, and you're not going to produce an organic molecule. You're going to produce carbon dioxide and water, and you're done. You can't get it back to be an organic molecule. But if you want to kind of play in the organic chemistry arena, you can take an alkane and go all the way to a carboxylic acid, or you could reduce this back to an aldehyde, to an alcohol, to an alkane. So here's an example: methane, methanol, methanal, methanoic acid. And then if you burned this, you would get an inorganic compound, carbon dioxide. All right, here's a simple, I won't necessarily even call this a reaction, but just understand that this is what's happened. If you take a carboxylic acid and put it in water, it will dissociate into ions. The hydrogen ion, this is what makes it acidic. This is an acidic hydrogen. And a carboxylate anion. So you're getting a hydrogen cation and a carboxylate anion. And what you have here is these equilibrium arrows, which are saying that these three species in the water are in equilibrium with each other. And generally, over 90% of the carboxylic acid is in this form, undissociated. And well, actually, it's like 99% for vinegar, for example. 99% of it is floating around as this molecule, and 1% of it has dissociated into ions. That is what makes it a weak. This is why these are weak acids. Let me just take you back to 1305, for example. This is a strong acid. Hydrochloric acid, 100% dissociation. So you don't see arrows going back and forth. What you see, every bit of HCl you put into the water becomes hydrogen ion and chloride ion. So this is a strong acid. You don't put this on your salad. If you do, you watch the lettuce disappear. You go, why is my lettuce disappearing? Well, you just put a strong acid on there. It's going to eat it up. All right? We can't tolerate this. We can tolerate this in our stomach. We can't tolerate it in our mouth and our esophagus. It will burn the tissue.
What does the R stand for? Is it just like a spot for like
R is just a general term for any carbon, any number of carbons. All right? So this is a general formula. If R is a methyl group, that's acetic acid. If R is an ethyl, it's propanoic acid. So R is just a general, they do this throughout the whole chapter, the whole book. All right, so these are weak acids. This thing here will have a pH of less than 1, and these carboxylic acids will have a pH of approximately 3 to 4. So they don't have as low a pH. And we can tolerate that in our mouth. This you know, it tingles, it tastes, it has a taste to it, but it doesn't, doesn't react with the tissue, doesn't injure the tissue. All right, so because they are weak acids, acids react with bases to form salts and water. This is also what you learned in 1305. An acid plus a base yields a salt plus water. All right, here's our base, sodium hydroxide. So a carboxylic acid plus sodium hydroxide will form a sodium carboxylate and water. You can see this hydrogen has been replaced by that sodium, but now as an ion. We have a carboxylate anion and an Na plus cation. So if we had acetic acid plus sodium hydroxide, we would get so this is acetic acid. It's also called ethanoic acid. And what are we going to get? We're going to get sodium acetate or sodium ethanoate. All right, we'll get into the naming of these a little bit more, but so that has those two names. We're naming the metal ion. Sometimes you'll see a plus here and a minus here just to show you that it's a ionic salt. All All right, there are some interesting salts of carboxylic acid. Sodium acetate, sodium benzoate. Look at some labels. You can see sodium benzoate. It'll say a preservative. Sodium benzoate added as a preservative. Coca-Cola used to have this in it, but they have replaced it. I don't know when, probably 5, 6 or more years ago. There were some concerns about with heat and with the acidity that Coca-Cola has, that can decompose into benzene. So they took that out as a preservative. I don't particularly like to see it in foods and things like that as a preservative, but it is in there, sodium benzoate. So preservatives, there's other preservatives that might be a little bit better, like calcium, sodium propanoate. This here is, athlete's foot ointments and things like that are a metal salt of a carboxylic acid. This is zinc. This is not I don't know what that number is. Is that 8? Yeah. 8 carbons, 9, 10, 11. So that's 11 carbons long, and you've got the zinc ion in there, and it can kill athlete's foot. It's an antifungal. Buffers. These are buffers. So if in foods you want the food to stay at a certain pH, they'll put citric acid and sodium citrate. The sodium salt of that acid and that acid end up forming a buffer. And it'll keep the pH at a certain pH. All right, why don't we finish a couple of those reactions. Let me see, where do we get into esters? Oh, there's polymerization. All right, let's do, let me just mention this, and then I'll go back to this slide and have you try to finish those reactions, and we'll keep esters for Monday. We'll pick up with esters. So we will have gone through what carboxylic acids are and how they react. Here, this is just kind of interesting. We looked at lactic acid a minute ago. Here's lactic acid. You can take lactic acid and polymerize it and form PLA, or polylactic acid, which is a biodegradable plastic. You can make a plastic film out of this. So it's not plastic per se, but it looks like plastic, but the beauty of it is that bacteria will decompose this. So it's not like a Ziploc baggie that you put in landfill, and 1,000 years from now they're going to pull it out and they say, wonder what they use these for. You know, but they don't degrade. But this one will decompose back into lactic acid, and bacteria can digest this stuff and survive on it. Who's the Lay's potato chips, I guess it was? They came out with Sun Chips back about 5 or 6 years ago, and they were trying to package them all in polylactic acid. So that it was kind of on Earth Day that they launched this, basically saying, we're trying to package our potato chips in a material that will decompose in compost piles and things like that. But they had trouble getting enough supply of this polylactic acid. One way you can make this is from potato peelings. All right, McDonald's gets a lot of potato peelings. You can ferment those and make lactic acid, and then companies would take that. Almost any organic material can be fermented down into lactic acid. Okay, while you're trying to scratch out those reactions quickly, I'll hand out chapter 14 homework, and we'll make a few other comments and be all set. I don't have, does anybody have the big document? Oh, is that, it says July 3rd? Wow. Wow.
But that's because we changed the.
Yeah. It probably, oh boy, probably gonna be more like July 10th. Yeah, we did get set back a little bit. I don't think we could, but we still need chapter 15. So on Monday, we'll do Esther's. Monday's the 3rd. And Wednesday is the 5th, we'll do chapter 15. And then I guess the exam will be
The following Monday.
on the 10th. Yeah, I didn't realize it was gonna push it off another whole week. So on the 10th, then we would get into, we'd have the exam and we'd get into sugars, we'd start biochemistry on the 10th. Yeah. Yeah, I think we could catch up from there. All right. For the top reaction, there's probably two acceptable answers to that. What do we have there? We have a primary alcohol, right? So, and we have an oxidizing agent. So that can produce what two things? What two things can you produce from a primary alcohol by oxidizing a primary alcohol? An aldehyde and a carboxylic acid, not a ketone. You can form an aldehyde, and what is it we got there? 4 carbons. So we can form an aldehyde. And then from that aldehyde we could form a carboxylic acid, or it can go directly through to the carboxylic acid. Now when you oxidize an aldehyde, what's the only thing you can make out of that? The what? Yeah, the acid. So here we've got an aldehyde. We got 1, 2, 3, 4, 5 again. Well, there's 1, 2, 3, 4. Now notice down below there we got 5. The middle one has 5 carbons. So that'll form a different carboxylic acid. But that's about all you can make with the aldehyde through oxidation. And the bottom one, we have propanoic acid or propionic acid. And we're reacting with potassium hydroxide. This is a base reacting with an acid. Now we're not going to get a sodium on there, we're going to get a potassium on there. and then water. All right. So on Monday, we'll pick up with the esters. Let me just go back and point out this slide here, okay? You should be, when I say make 3x5 cards, you know, I kind of mean it. Each one of these chapters, make sure you soon take some time to sit down and make these 3x5 cards. At the end of the course, on the final exam, well, on exam number 2, these kinds of molecules could be on there, and they could be saying some things like complete the reaction of acetic acid with the acetic acid with potassium hydroxide. You're going to see, we'll talk about esters, so you'll have to start being familiar with writing out reactions of acetic acid with alcohols to form esters. So be familiar with these. These are very, very common. Acetic acid, extremely common. Common name of a compound.
So you just want us to know the name and the structure?
Name and the structure. Both the common name and the IUPAC name and its structure. All right? Okay, I'm going to release you to get into your teams in the tutoring center, in the library, in the hall, wherever you want to. Work with your teams. Does everybody know what team they're on and what their team is on? What their team is focusing on? So start pulling some information together. One of you should be trying to get it into some 3 or 4 PowerPoints. And if you want to sit down with a laptop, even right in these 30 minutes, and type some things in and get a few slides together, later on in the semester we'll be sharing that with the class, all in one day. All right, I'll see you Monday. I don't think so. Well, look up different artificial sweeteners and particularly focus in on how they affect your health. The impact on health of artificial sweeteners. And so, for example, you might say, okay, try to find out what are